This video is homework help for homework 4C for Math 200. All of the problems in homework 4C have a common theme to them, and this is what it is. You have a practical problem. The first one is from construction, the second one is from just energy expenditure, and the third is from economics. And you write this problem as a function of one variable. That takes a little bit of algebra and thinking, but you can get it as a function of a single variable. Then you look for the maximum or minimum values of that function, and you use calculus to do that. So to find the max and min, the first thing you do is take the first derivative of this function. You take its derivative and you set it equal to 0. This is a critical point. Now you don't know whether it's a maximum or a minimum. To find that out, you take the second derivative and you evaluate that second derivative at the critical point. You found this critical point here, and that's where you evaluate the second derivative. If the second derivative is positive, then the critical point is a minimum. If that second derivative is negative, the critical point is a maximum. So that's basically what we're going to do. Start with a function, take the first derivative, set it to 0. Take the second derivative, evaluate it at the same place. Find out if it's positive or negative. So I'll do this one in pretty much in detail. The others will be more sketchy, but you'll get the idea. So this is from construction. You have this log, and you want to cut from it a beam, a rectangular beam. So here's your log, and your beam is inside of here. It's a rectangular beam. The drawing has 12 in it because I stole it off the internet, since I can't make my own drawings very well. And but let's replace a 12 with h. H will just be hypotenuse, right, for this problem. Now the first thing to do is write the function, and you're given some information here that the strength of the beam is proportional, not equal, to the width times the depth, the square of the depth. You did some of this in algebra, but as you know, when you study the next subject, then you learn the previous subjects much better than you did when you were studying them. So we're looking back into algebra now and saying, how are we going to write this? Well, I'll use some kind of symbol for strength. Obviously, I'll use S. Then I know it's proportional to width times d squared. All right, it's not equal to it. It couldn't even be equal. Look at what are the units of width times depth squared? Well, if these were feet, that'd be feet cubed, which isn't a unit of strength anyway. Okay, so to fix that, it becomes equal if I give it a constant of proportionality k. K is just a constant of proportionality. Probably, maybe it's different for different wood, probably. Okay, so k is your constant of proportionality, and it has to multiply. I have to put the LT down here because I ran out of room there. Okay, width times depth squared. Now for the stiffness, I don't want to use S again, so I'm going to use T because that's the second letter here. Again, it's proportional with some K. These K's are not the same. In fact, you could have used a C, I could have used a C, or some other letter. You could have used alpha, doesn't matter, but they're not the same, but it's not going to worry, it's not a problem right now. So the stiffness is proportional to the width times the depth cube of the depth, so times the width times the depth cubed, and those are the two equations that I have here. These are functions of two variables. They're a function of width and they're a function of depth. Now, following the instructions in the problem, you can turn this into both of these into functions of a single variable. The single variable that we're going to use is the angle here, so called theta. Remember, this is h. Okay, and we'll use trig functions. What's the cosine of this angle? It's w over h, and the sine of the angle is d over h. All right, so the width is the hypotenuse times the cosine of theta. the depth is the hypotenuse times the sine of theta. You could say that h is another variable, but let's just leave it alone. If we're really thinking of the angle. For example, is this beam, would this be a better beam? So theta would be different here, your width would be different, and your depth would be different. That's what we're asking. Don't worry about, we'll say it's out of the same log, so h is going to stay constant. Right. Now to use these, I take the original equations, which I've given right here, and substitute for the w and substitute for the d. So I've got k, here's my substitution for w, here's my substitution for d. Work out the algebra, and I get k h squared cosine theta sine squared theta. Oh, there should have been a k here, sorry. All right, and now for stiffness, same thing, but I've got a w and a d cubed. So I have, here's the w, here's the d cubed, and when I work it out, I get k h to the fourth cosine theta sine cubed theta, and earlier versions of the homework show k h to the fifth, and if you have one of those, that's an error. So the hint that I gave you was sort of a red herring more than a hint. Right. Now we have the stiffness, the strength of the beam in terms of angle, and the stiffness of the beam also in terms of angle. And those are the functions we were looking for. For this problem, we're looking for maximas. We want the maximum of the strength and the maximum of the stiffness. And we're treating those as two separate problems. Don't even try to put them together. You're just going to find the stiffest beam and the strongest beam. So let's do the strongest one first. So here was our equation from the previous slide. Strength equals k, that constant of proportionality, h squared cosine theta sine squared theta. Right. Now this is a style point, and I think it's a good idea. You see this kh squared? Those are constants. They're constants, and you can, one way to handle them is just to leave them on this side. Another way to handle them is to throw them over to the other side and get them out of the way, so that all you have left are the variable of interest, the thetas. Right, and that's what I do, and you'll see people do this in physics and engineering as well. You just take this, you divide both sides by kh squared, assuming they're not zero, which would kind of make your problem vacuous, and you just put them on the other side. They won't matter over there, and you can always bring them back to the other side if you want. So now I'm just taking the derivative with respect to theta of cosine theta sine squared theta, and I don't have to worry about those constants. This is also, well, all these problems are good exercise in ignoring variables that are constants, or rather treating them as constants. Okay, so now I'm going to take this derivative, and I'll have to use the product rule, because these two, and I'll have to use the power rule also on the second term. So the product rule says hold one of them constant, so here I'm holding the sine squared constant, and take the derivative of the cosine theta. Derivative of cosine theta is minus sine theta. Now I hold the cosine theta constant and take derivative of sine squared theta. I'm using the power rule inside the chain rule. So cosine squared, the 2 is going to come out in front, and I get sine theta. Then I take the derivative of cosine squared. If you're not sure about that, you can think of it like this. Sine theta squared would be 2 sine theta to the 2 minus 1, which is 1. Now the inside function is sine theta, and its derivative is cosine theta. In this form, it's very hard to see what's going to go to 0 or not, so simplify it. And I simplify it by seeing I could factor out a sine theta, so I do that. Here's my sine theta, then in parentheses I have 2 cosine squared theta minus sine squared theta. Now this is another sort of style point, but it is important. I'll have a negative sign in front. it's very awkward to have something, well, it wouldn't matter if it's this term, but something in a parenthesis start with a negative sign. It almost looks like you're subtracting it, right? So it's better to write the positive one first and then the negative one. Right, so this is my first derivative. My constants are sitting over here in storage, so to speak, and I get sine theta times, and then in parentheses I have 2 cosine squared theta minus sine squared theta, and I'm going to set that equal to 0. So again, just to reiterate, I had some information about how a stiffness of a beam that I can cut from a log, and I write that in terms of one variable, and the variable I'm going to use is theta. Okay, I take the first derivative looking for the critical points, and then I will take the second derivative after that. So what I'm doing here is setting the first derivative, and if you're troubled by these constants over here, if this is 0, 1 over kh squared ds by dt is also 0, so it doesn't matter about the constants. So here are the terms I'm setting to 0. Well, if you have true terms multiplying each other, like say AB equal to 0, one solution is A equals 0, that will work, and the other is B equals 0. So in this case, we'll say this is A and everything in parentheses is B. So if I set sine theta equal to 0, I get results that are not practical. For sine theta to be 0, theta either has to be 0 or it has to be pi. Well, if theta is 0, here's the, okay, change. Okay, so here's this beam that I'm cutting. Oops, sorry, went over too far. Okay, if theta is 0, that means I'm cutting a sliver, right? Because theta is this angle down here. That doesn't make any sense. If theta is pi, it's still a, that doesn't make any sense. So I'm just going to reject that solution as impractical. Now I have to take what's in parentheses and set that equal to 0. And that's going to take a little bit more work. And I'll show you the steps. So here is the function we're trying to set equal to 0. There's one way to do it that's, in this case, will work out. But technically and theoretically, it is incorrect. And that is to divide both sides by cosine squared theta. Okay, so you're going to multiply them by 1 over cosine squared theta, and then you'll end up with only one trig function. The idea is to end up with one trig function. That will just give you a tangent. Okay, it will work. However, when you do this, at this point you don't know what's going to drive the whole thing to 0. And if this turns out to be 0, then you've divided by 0, and that's a big problem, right? It's an error. So it's better not to divide by something for which you don't know the value if it could possibly be 0, and cosine is 0 quite a few times. Okay, so we're going to do something else. What we're going to do is use trig identities. Now the goal here, let's see, look again at this equation. You've got sines and cosines in here, and that makes things very awkward. If you have an equation that you're trying to set equal to 0 with a bunch of trig functions in it, try to use these trig identities so that all the trig functions become the same. And what we have here is cosine squared and sine squared. You can go look in the front part of your trig book and you'll see a whole list of these identities. And notice that cosine squared can be written in terms of cosine 2 theta, and sine squared theta can be written in terms of cosine 2 theta. When I use these, I'll only have cosine of 2 theta in the whole equation. Only one trig function, cosine. The 2 theta you can deal with later. Okay, and here are the identities, and I'm going to substitute them into this equation. So for cosine squared, I put this. For the sine squared, I put this right here. Okay, set that equal to 0. So here is my equation. I readjusted the screen. Sorry if that looks sort of awkward there. That's because the solution was falling off the end of the screen here for Camtasia to record. Okay, so I did the substitution. I have everything in terms of cosine 2 theta, and now I just work out the algebra. If I multiply through by 2, I get 1 plus cosine of 2 theta. Carry the negative sign through and I get minus 1/2 plus 1/2 cosine 2 theta. That all equals to 0. Okay, so I've got 1 minus a half, so I've got a half here plus 3/2 cosine of 2 theta. Put the half on the other side, then multiply by 3 over 2, and you get this equation. Cosine 2 theta equals minus 1/3. Now if you forgot what we're doing, we're trying to find the value of theta that sends that first derivative to 0. But after we took the derivative, we're just taking the different factors of it and setting each one to 0 to find an answer. Right, so can we solve that? Yes, we can take the arc cosine of both sides and we get 2 theta equals the arc cosine of minus 1/3. And from your calculator, that's 1.91 radians, or if you're working in degrees, it's 109.5 degrees. Divided by 2, you find out that theta is 0.955 radians, or 54.7 degrees. Now this is the value of theta that would set the strength equation to 0. I'm sorry, the derivative of the strength equation to 0. Right. So if the strength changes with theta, let's say there's some graph like this. Here's theta, and here's the strength of it. Let's say as theta increases, it goes up to some maximum, and then it starts coming down. All right, this peak could be at 54.7. Or, and we don't know this yet, perhaps the strength was going down and coming back up, and at 54.7, it's a minimum. So we found the place or places along the curve for the strength in terms of theta that are going to be peaks or valleys. We have to find out which it is by taking the second derivative. So here I am taking the second derivative with respect to theta. Those constants just hang out in the front, they're fine. Second derivative of the strength equation is what I'm looking for, which means I'll take the derivative with respect to theta of what I got for the first derivative, and here was the answer for the first derivative. Now to take this derivative, these are two terms multiplied together. I'll need to use the product rule, and later on I'm going to have to use the chain rule. Okay, using the product rule, I hold, let me get this cleared up a little bit. Okay, I'm going to hold this constant, that's what's going to happen here, and take the derivative of sine theta, which will give me cosine theta. Okay. Then I hold sine theta constant, and I take the derivative of what is in the parentheses. For the first term, I have to use the chain rule. So this is cosine squared, so the squared comes out in front and multiplies the 2. That's where I got the 4. Then you still have cosine theta from the chain rule. Cosine theta is the inside function. You take its derivative, which gives you sine theta, but that's negative, and I put the negative out in front. The next term, again, the chain rule, well, the power rule with the chain rule. The 2 comes out in front, that's where the 2 comes from. Sine theta is still here, and now here's the derivative of the inside function. Sine theta was the inside function, and you get cosine theta. All right, in the previous slide, or a couple slides ago, I said don't put a negative sign right at the parentheses, and that's true, but I did it this way just so that you can map out the steps. Other thing I want to note on here is something that unfortunately I have not been able to really communicate to people very well. Some people are very good about it naturally, and others need to learn it. And that's when you write equations, you're not writing them as in previous, like more arithmetic classes, where the person only cared that the answer was 25.7. I don't care about that. I want to see your steps. I want to see your work. And so will anyone for whom you're doing a problem like this. They don't care that you came out with theta equals 54. They don't care. They want to see your work, because that's where any errors are going to show up. And what if you made an error and then corrected it later, but you use that procedure on a different problem and the correction doesn't happen? Okay, so you want to see the steps, and what's really important in showing steps is that you write what you're doing. Don't just start derivative of this and write, and just, for example, don't just write this out somewhere on a piece of paper. You don't even know where it came from. I know I'm lecturing you. You don't even know where it came from a week later. You won't even know where you got it. But when you write a term like this in front, it says, I'm taking the second derivative. I'm taking the second derivative with respect to theta, because when you get to calculus 3, you're going to be taking derivatives with respect to several variables. So it might be x, y, z, t, who knows what variables, and you have to always specify those. So it's good to do it right here. You're taking the derivative with respect to theta. It is the second derivative. It is the strength equation. All of that information is right here, and it equals what it's equal to. Anytime you write an equal sign, make sure they're equal. Some people like to use arrows. Arrows are good for certain circumstances. Try to use equal signs. Right. When I go to the next line, you on paper don't have to repeat this. I had to repeat it because of the software that I'm using. It takes more time to line up those equal signs, so I did it like this. You don't have to write it the second time, but you can write an equal sign on the next line and continue your calculation. Every equation between the equal signs are all equal to each other. Right, so that's important, and it's good to see this. This is how I do it, and they do it in publications, and you should do it also, just as a habit for yourself as well as for the person you're working for. All right, so now let's go back to what we're doing. We're taking the second derivative. We took the second derivative. We used the product. We used the product rule, and then we used chain rule. Okay, so now we have all these terms, and we want to find out if those are going to be positive or negative. You could just substitute at this point, but it's very awkward. It's much better to work out your algebra and write a simpler equation. So I did that here. Okay, you can see I multiplied the cosine squared here, cosine onto cosine squared, and I got the 2 cosine cubed. Then if you work out these other terms, you end up with minus 7 cosine theta sine squared theta, and that's a lot easier to work with. You should try to work it down to that level. All right, you could factor out a cosine here, but it doesn't matter. Okay, this is what we've got now, much better. Now we want to evaluate that at that 54.7 degrees or 0.955 radians. This is the value of theta where the first derivative evaluated at 0.955 was equal to 0. This is the critical point. So I take the 0.955 and I substitute it for my thetas in this equation. And when I do that and work through it, I find that the answer numerically is minus 2.3. That's less than 0. So you have the first derivative 0. At that point, the second derivative less than 0. That means the curve's doing something like this, and it's a max. This would be the strongest. This angle would give you the strongest beam cut from that log. Now here's the second part of problem 1. In this case, you repeat the steps, but you do it for the stiffness of the beam. Now let's remember what the equation for the stiffness was. Okay. Some constant times h to the 4th times cosine theta sine cubed theta. Unfortunately, I didn't write it here. I should have. All right. So this is our new equation, our new function we're working with, and it's the same procedure. Find the first derivative, set it equal to 0. Find the second derivative, evaluate it, and see if it's positive or negative. And I'm not going to do all the steps here, but it's going to be the same procedure. I'll do part of them. So I'll take the first derivative, and when I take the first derivative, again, I use the product rule, and then I'll have to use the chain rule for part of it. Okay, so here is the first derivative. I try to make it in a little bit easier fashion by some algebra, so I have to set it equal to 0. Actually, I can factor out the sine squared and I'll be left with sine squared theta, and in parentheses 3 cosine squared theta minus sine squared theta equals 0. Now by matching the steps, you can continue to solve this problem and find the value of theta that will set that equal to 0. It's very similar to the first example that I worked out in detail. Also, you use exactly the same trig functions, the trig identities, to get everything in terms of cosine of 2 theta. Your numbers are a little bit different, and you end up with, I'll give you the answer so you can check it, it's about 2.09 radians. Okay. Now you take the second derivative and you evaluate it at 2.09 radians. Make sure your calculator is on radians if you're using radians, or degrees if you're using degrees. Okay, so you don't switch around in the middle of that. So at any rate, you look for the second derivative. So I'm going to find that second derivative. And again, I keep the constants over here out of my way, and I evaluate it, find it, evaluate it at this value, and see if it's positive or negative. The second derivative will be negative, and so at that point, and so it is a max. Okay, so I think you can do that one yourself.